example of kind of analog in this sense. And last but not least, here is a symbolic model. Now, I hope this doesn't frighten you. This is a very simple mathematical equation. All it says is that change in population over time is proportional to population. In other words, the amount of population growth is proportional to the population that we've got. So that's a growth rate. And what it leads to, if the growth rate is positive, that is classic exponential growth. And there are many models in our field. For example, Forrester's urban dynamics model, the whole systems dynamics movement, in some sense, is based on the idea of these simple differential equations that lead to growth or decline, or in fact, logistic growth, S-shaped growth, if you put some capacity constraint. Now, these are computable models in the sense that once we've fitted the model to a particular system in that sense, then we have very strong predictive capabilities in the sense that we can make forecasts for the future. We change time and we change the growth rate, and we find out what the population is likely to be in the future. If you fit this curve over the last 10,000 years, or the last 100,000 years, then you see a superb, well, it's actually a double exponential growth to the top. In fact, what's actually happening is that we're just about to tip over the top. This is a digression in this lecture, but in the next 20 or 30 years, we will no longer experience growth. Population growth will peak at about 9 or 10 billion in the world, so all the recent forecasts show, and we'll enter a regime over the 21st century which is quite different from anything in the last 10,000 or 100,000 years, or even the last million years in this context in terms of the growth of human population. So, to some extent, again, another excellent example. If we looked at the past, we'd see exponential growth, but we know, because of what's been happening quite recently, that that's likely to tip over. Okay, now, modelling and computation. Now, I've really said all of this. Computers came out of the Second World War. They came out of the Manhattan Project in the United States. That's von Neumann and Los Alamos. It led to the bomb. It came out of Bletchley Park, with Turing and various people cracking codes about German submarines in the North Atlantic, and then Konrad Zuse in Germany in the period 1940 to 45 also developed a digital computer in that sense that was part of the war effort there. So to some extent, these machines were really developed, or the impetus for those sort of the innovation of building computers came out of the war. And as soon as I said, as soon as they came out of this context, then they began to be applied to more practical applications in terms of social and economic applications in this context. Now, I've really talked all about that. Let me actually show you an example of what's been happening in terms of the spread of these models, in terms of the idea of the analog model, as it were, and the iconic model being turned into kind of some sort of digital medium. Think about iconic models as being models like this. Think about symbolic models, think about analog models in that sense, and then think about models, digital models in this sense, and then think about how they're beginning to converge. Now, here's an example of the kind of media that if you go back to when Larry wrote his paper, and I was a student in those days, no one ever expected the idea of the architect's model to be made digital in some sense. So here, for example, on the top left-hand side, we see a CAD model of London, and an extruded model. I'll talk over it in a moment and show it running in that sense. And once we have that model, which is built in ArcGIS, it's built through remotely sensed data. You can build it in about a couple of hours now if you've got the data. The model has something like 3 million building blocks out to the orbital road, out to, many people here have probably been through Heathrow Airport. If you think of the model as every building block in the city from the digital database extruded using remotely sensed LiDAR data, then that's essentially what you see, a little bit of cleaning, and one or two symbols, etc., a little bit more detail, etc. But by and large, this is the block model. Once we have that model built in ArcGIS, we can import it into lots of other media, and then you see on the right-hand side it being imported into a virtual world, a virtual design studio, if you like, where the avatars are people like ourselves logged on from remote locations, showing this context. So here's the model itself, to give you an idea. and of course it looks complex. It is, well, it's complicated in that sense, but it's relatively easy to manufacture in that sense. There are many of these things. When we first developed this model, it was quite innovative. We built it in sections to begin with, and one or two buildings, you can see this is Cannon Street, one or two buildings in the City of London are rendered in more detail, because once you have a CAD model of the building, you can probably slot it in. It can be transformed into an appropriate shape, a mod file or shape file or whatever, and it can be put into this particular media. You can see that there are not many, there's only about 50, this is the central London version of our model, there's about 50 or 60 buildings that are rendered in more detail, but most of it's a block model. And our interest in this model is actually beginning to represent things that go on more in symbolic modelling and to embed them in this particular context. There's St Paul's Cathedral, the Tate model and so on. Okay, let me move on. Okay, we build the model in layers in that sense. So here's the digital terrain model. We paste a photograph and a photograph across the top to give it some sort of texture in that sense. And then we extrude, as it were, the building blocks in this sense from the bottom up. One of the nice things about the model, and this really relates to the power, and this has not been done very much, is that each of these individual buildings can be switched on and off. And if we have 3 million buildings, I should say there are not 3 million buildings here, there's probably something in the order of about 1 million building blocks, because the other 2 million bits that are picked up by the extrusion and the LiDAR are things like chimneys and greenhouses and things of that sort. But the true building blocks that we would think of in terms of an urban planning application, the parcels in this particular context, are about 1 million out of 3. Now, the point I was making is that we can switch these buildings on and off. Think about 1 million buildings and all combinations of buildings being switched on and off. The idea of different city forms in this context, here we have an incredible laboratory where we can actually explore many possibilities. Now that's just by switching the existing buildings on and off. The reason why we switch these two on and off is that these are the two buildings that were developed by Norman Foster. One is the GLA headquarters, Great London Authority headquarters down at the bottom. That was the kind of circular building, that spherical building. And then you have the new icon of the central London skyline, which is the Gherkin in that sense. One of the interesting things is that we can do many things with this model. For example, we can actually sort of layer different other layers. This is nitrogen dioxide layer layered on top of it in that sense, and I'll come back to that in a moment. But we can also flood the model in that sense. So here we've actually raised the Thames by a metre or so, and we've simply introduced the layer so that you can see that the battleship is anchored off as a tourist attraction. Up the south bank there is, looks as though it's floating. Of course, it doesn't float in a sense, we're just raising the layer. So it's not a true flooding of London in that sense, but it's very evocative in that sense. The other feature, of course, is that this little building at the bottom, built by Norman Foster, where the GLA headquarters is, that's the Greater London Authority, which is the municipality controlling the whole lot, is actually flooding. If you ask the question, why did this land remain not built on for many years, for 2,000 years, etc., it's largely because it flooded, but, and you can see that certainly this gives the impression of flooding. Okay, let me show you this notion about how these models are coming together. We have a model, or we worked with a project that has a model, which is an air pollution model of London, the ADMS model, and there's a group at King's College which, and I'll just load this, in a sense, I think I've probably got it loaded already, the air pollution movie, if it comes. We worked with a group at King's College, and this is always difficult. I seem to have now got my PowerPoint into my QuickTime movie, so